Okay, welcome everyone. So you've all finished the first exam. Hopefully that went okay. I'll try and have that back to you in a reasonable amount of time. So we'll just go ahead and continue on our lecture about additives. I have gone through and edited out some slides. So if you're looking at the slides on Canvas, you'll notice that we will skip some today so we can get through everything. So this is where we ended. We're talking about antioxidants. So remember to fix that there on how to choose which antioxidant you want. So you generally want to match the continuous phase of an emulsion. So if you have a oil and water, water would be the continuous phase, so you want a water-soluble antioxidant. And if you have water and oil, oil's the continuous phase, and you want an oil-soluble antioxidant. So we have two antioxidants that don't really look like antioxidants. One of them would be sulfites. These are several different salts and even a gas there, sulfur dioxide, that are added to food as to prevent oxidation of specific things. The reaction down there at the bottom is just to show you that no matter what form the sulfite is in that you add, if you add a metabisulfite or if you add sulfur dioxide, once these sulfites are in aqueous phase in that food, then they just freely convert between each other. And so there isn't really going to ultimately in that food be any differentiation between any of those different sulfites that you add. But sulfites are specifically used to inhibit browning reactions in food. And they will inhibit both enzymatic and non-enzymatic browning. We will talk about enzymatic browning when we are in the enzymes chapter. But right now, enzymatic browning is the browning that you see in apples and lettuce, some different kinds of fruits and vegetables that turn brown over time once they are exposed to oxygen. And that is catalyzed by an enzyme called polyphenol oxidase. And so by its name, the phenolic compounds in that food are converted into quinone compounds. And what sulfites do is they convert those quinone compounds back to phenolic compounds. So they reverse that reaction. So that's one thing. They also, the polyphenol oxidase has copper as a cofactor. So it has copper chelated in that protein. And sulfites can remove the copper from that active site. And so they both reverse or consume the product of that enzymatic reaction so that it won't polymerize and turn brown, but instead goes back to the original compound. And then they also inhibit the actual enzyme by removing the cofactor that's required for it to work. For non-enzymatic browning, here we're talking about reactions with sugars and amino acids. So sulfites inhibit non-enzymatic browning several ways as well. So the first way would be that they can react with aldehydes, and in doing so, they prevent those aldehydes from now reacting with the amine groups there. So we prevent the Maillard reaction because we have prevented the reaction of those aldehydes with the amines. They can also react with hydroxyl groups on carbohydrates and form sulfonate compounds. So basically, that hydroxyl group now has a sulfur group attached to it. And when that happens, these the decomposition products of those sugars are less reactive. And then you remember we've talked about that in the process of dehydrating that sugar, we create a lot of dicarbonyl compounds. And those dicarbonyl compounds are really reactive. They participate, for instance, in Strecker degradation to give us flavor compounds. But sulfites will reduce those carbonyl compounds. So they are no longer, they're less reactive. So a couple of different ways there, specifically targeting those sugars. So reacting with either the aldehydes or the hydroxyl groups on those sugars to prevent them from being so reactive. The second compound that is added to foods sometimes that has some antioxidant activity would be nitrite, a compound that doesn't necessarily seem like an antioxidant. So nitrites, of course, added to cured meats to prevent Clostridium botulinum growth. But they do have some antioxidant properties as well. So in this reaction scheme on the left here, you see that, first of all, that if we add nitrate, so NO3 is nitrate, NO3 minus is nitrate. If we add nitrate to food, over time, from microbial action, it will be converted to nitrite. This is NO2 here. Nitrite is the compound that is performing the function that we've added it for. So nitrite is what we need to have in that cured meat to prevent Clostridium botulinum growth. So that's why it's added. Typically, just nitrite is added, not nitrate. But sometimes in a fermented meat, something that's going to be fermented for a period of time, then nitrate might be added, and then ultimately it's converted to nitrite. But anyway, we have here nitrite. This is a picture of nitrite here. So if you look at this picture, can you imagine that this compound can be a chelating agent? If we had a metal right there, we could chelate between these two oxygens and form a 5-membered ring, chelate. So it can chelate metals, that's one thing. So once we have chelated those metals, then those metals are not going to be pro-oxidants anymore. Okay, so first reason that this can be an antioxidant would be that this nitrate can chelate metals, and particularly we're talking about iron here, because we're in meats. Okay, in addition, that over time, at the pH range that we have typically in meat, the nitrite is ultimately converted to nitric oxide, this NO here. And nitric oxide, here's a picture of nitric oxide right here. And what you'll notice is that it has an odd number of electrons. And so this can be an electron donor or acceptor. And so it can act as an antioxidant by donating that electron to a free radical that would have an unpaired electron. So there's the second reason that nitrate can be an antioxidant, and that would be due to this nitric oxide having unpaired electron there that it can donate. Nitric oxide in meat also will react with the myoglobin, and specifically the heme compound there. So you see this picture here with nitric oxide bound to the iron. And when it binds to this iron here, that's what forms the pink color that we see in ham and bacon and those kinds of cured meats. But when this binds, you can think about it as locking that iron in place so that the iron is not going to come out, possibly, and be a pro-oxidant. So once that nitric oxide binds to that iron, it's very stable, and it's not going to leak, not going to come off of that heme ring there. Okay, so 3 reasons there. Chelator, electron donor, and then this, I guess, would be a chelator again here, preventing that iron from coming out. So now let's talk about some antimicrobial agents. So a different kind of preservative. So instead of preserving the food from oxidation, now we're preserving it from microbial growth. So fatty acids themselves can be antimicrobial agents. So this is both short fatty acids and long fatty acids can be antimicrobial agents. Typically, we don't have lots of fatty acids around in food. So this is, maybe not as interesting, but certainly there are some rules here. So unsaturated fatty acids, like we saw linoleic acid and linolenic acid in the flavors chapter. So those would be unsaturated fatty acids. So those would be most effective in the free fatty acid form. Medium chain fatty acids, so the capric acid that was on your study guide, I think, and also some other medium chain fatty acids like lauric acid and myristic acid, which we'll talk about in the lipids chapter. So you don't necessarily need to know them now, but most effective in the monoglyceride form, so esterified to glycerol. And then this is the mechanism here, so it's just going to interfere with that lipid bilayer and transport of compounds across that bilayer. More often, when we think about antimicrobial agents, we think about short, small acids, like acetic acid or lactic acid. So here is what those acids do. So these are weak acids, right? So when we put them into water, they're going to dissociate partially. So we will have some of the deprotonated version and some of the protonated version. And that protonated version is nonpolar. So you think about like acetic acid, that once we put that proton on there, it's going to lose its charge. It's going to be much less polar. And so now it can migrate through the lipid bilayer of that cell inside the cell. And once it gets inside the cell, it's going to do the same thing that it did outside the cell, which is partially dissociate. And when it does that, it's going to release some protons and lower the pH inside that cell. And if it does this enough, it's going to overcome the buffering capacity of that cell. So the cell is no longer going to be able to keep the pH that it needs to survive. instead that pH is going to drop. And so instead of being pH 6.5, it's going to be something lower than that, which is going to be damaging for that cell. I have this here showing that, once this acid deprotonates and becomes charged, it's not going to go back outside the cell because that strong charge is not going to migrate through that lipid bilayer, that really non-polar lipid bilayer. So basically, it gets locked inside the cell. And as more and more of this goes inside the cell, more and more gets locked inside the cell, and the pH drops more and more, and ultimately kills the cell. So this is typically what we think about when we think about these small acids, small organic acids being antimicrobial agents. And the most popular ones would definitely be acetic acid and lactic acid. These would commonly be used as antimicrobial agents. There's another short chain acid that is commonly used to inhibit mold and some bacteria, but certainly it's targeting mold. So that would be propionic acid. So this would be a 3-carbon aliphatic fatty acid. And it is added to baked goods. So almost everything that you purchase in the store, bread, muffins, cookies, cakes, not cookies, cakes, all of these things, any kind of baked good with moisture still in it is going to have propionic acid in it as a mold inhibitor. That's the principal way that bread goes bad is that it starts to grow mold on it. So this propionic acid is added there to prevent that from happening. So there's 2 things to remember here. Number 1 is that it must be acidic. So if you are at a pH above 5, propionic acid is not going to help inhibit that mold. So the pH must be below 5. The normal pH for bread and other baked goods is above 5. So all of these breads now, they need to have some acid added to them. So you will see in ingredient statements, you will have, acetic acid added there, vinegar or something like that. Sometimes citric acid is added. So all of these bread products that have propionic acid added as a mold inhibitor would also have some other acid there to bring the pH down below 5. So this is a special property of propionic acid, and it's due to the ability for this 3-carbon molecule to mess up the metabolism of 3-carbon molecules in that cell. So that's what it does. The usage is typically about 0.3% in baked goods. Usually it's added as a salt, so it's not typically added as propionic acid. It's usually added as calcium propionate or sodium propionate. In bread, like the picture that I have there, it's typically the calcium version. And in chemically leavened products, like cakes or muffins, quick breads, banana bread, stuff like that, it would be sodium propionate. Okay, another organic acid that's used as an antimicrobial agent is sorbic acid. Sorbic acid is effective against both yeast and mold. And by the way, I encourage you to keep track of which types of microorganisms each of these different acids inhibits. that is a question on your study guide. So sorbic acid is effective against both yeast and mold. Here's the mechanism here. This one is effective all the way up to pH 6.5. So most of the time we need the pH to be a little acidic for these to work. This one is unique in that you can get up almost to neutral and it's still effective. A common use for sorbic acid would be in this product here, bagels. So it's definitely in a lot of baked goods. So I have a question here. So you see this ingredient, yeast. So bagels and all these breads here, they're leavened with yeast. Sorbic acid kills yeast. So how in the world is sorbic acid used in, or why is it used in this product? If we're leavening this product with yeast, why would we add something that kills the yeast? So the answer is that sorbic acid is actually not in the formulation. So these bagels are made and baked, and then as they come out of the oven, they will go under a spray of sorbic acid. So the sorbic acid is only on the outside of these bagels. Of course, as they cool, then that spray will dry, and that sorbic acid will be on the outside. So it's going to prevent yeast from growing on the outside of the bagel, which is where it would grow. It needs oxygen. So, they're not actually inhibiting the yeast that was there to leaven the product. It's added after it's baked. And then, of course, very important to package all of these things without touching them. So machines would be packaging these so that we wouldn't get any yeast or mold spores from our hands onto the surface of that bread product. But this sorbic acid would provide a little bit of a protection against anything that might fall on it between the time it's out of the oven and in the package. Next, we have benzoates and also parabens. So these are similar type compounds. This top one would be a benzoate. This is benzoic acid, or this sodium benzoate. And then down here we have, this is the ester, the methyl ester version. This is a paraben. The methyl ester version is a paraben. So typically added as the salts, again, either sodium or potassium. And that is simply because they are more soluble than the acid version. Still not that soluble, but better solubility as the sodium or potassium salt. I don't have here on this slide, but the benzoic acid let me see here, must have a slightly acidic pH. So it's going to be effective about up to pH 6. And with all of these, I will say the lower the pH, the better. But you can go up to these higher pHs because a lot of these products they're used in are not naturally acidic. So with the parabens, though, those are unaffected by pH. They're active at all pH ranges because we have taken this acid group and converted it to that methyl ester. And so now it is not, it is not changed by pH. I mean, unless we went super alkaline, which we wouldn't in food. So if you have a product that's really at that neutral pH, parabens would be the choice to inhibit these yeast and bacteria. Sulfites, in addition to being antioxidants, they can be antimicrobial agents. Just like the acids, they're more acidic or more active at acidic pH values. They inhibit bacteria, probably interfering with disulfide bonds. Next, we have nitrates and nitrites, and I already mentioned they're added to inhibit Clostridium botulinum. So the active form is the nitrite. Remember that? Active form is this NO2. Sometimes nitrates are added, but that would be only if during the fermentation process of that meat, they're going to be converted to nitrite. Natamycin is a I'm not thinking of the word right now. This is the structure here. It inhibits mold, and it's commonly added to cheese, especially grated cheese, because in grated cheese it's much more difficult to see the mold there if there's any mold growing. In a block of cheese, it's very easy to see that mold growing on the outside, but in shredded cheese, that's much more difficult. And there's much more surface area for the mold to be growing. So this is very commonly added to prevent that from happening. Antibiotic is the word that I was trying to think of earlier. Okay, next we'll talk about alternative sweeteners. So just so you know, the slides on alternative sweeteners, I'm going to skip all those. So this is the only slide we're going to have on alternative sweeteners. But this is a nice summary slide. So first of all, we have several here. These are the sulfur-containing artificial sweeteners. And you'll notice here that they're all a lot sweeter than sucrose. So that's a common characteristic of all of these alternative sweeteners, is that if sucrose is 1, these are all going to be much larger than 1. So important to remember that these alternative sweeteners are much more intensely sweet than sucrose. So I'll give you a little example. So when I was in an undergrad, I had a friend of mine that was making chocolate milk that was sweetened with these artificial sweeteners. I think she was using potassium asulfame K here. And she knew that this was a high intensity sweetener. So the formulation called for 20% sucrose in the formulation. And so she took it down to 1%, knowing that it needed to be lower. And 1% seemed like a pretty small amount. So you see there on the slide, how much sweeter is asulfame K than sucrose? 200 times, not 20 times. So when she tasted that chocolate milk, it was, of course, incredibly sweet, but she was not able to taste anything but sweet for the rest of the day. So these are intensely sweet, and you really use such a small amount. Okay, and sometimes I will say it's difficult to grasp that concept. If you have used any of these products at home, the Splenda, that kind of stuff that you use like in the restaurant in those little packets, or if you buy a container of it in the store, those have maltodextrin in them as a filler. So most of what you're pouring on there is starch, hydrolyzed starch, not the actual sweetener. So that sweetener is just coated on that carrier so that when people pour it on, it actually looks like something. If they just gave the thing to you straight, you'd put on like a couple of crystals and that's it, and nobody would be happy with doing that. So, but when you're in the food industry, you will be working with the purified compound, and so you have to get used to that kind of thing. We have 3 sulfur-containing artificial sweeteners. 2 of them are approved in the US. Cyclamate we can't use here. Cyclamate is approved in many other countries, but not in the US. So just asulfame, potassium, and saccharin can be used. Next, we have the peptide sweeteners. So, of course, the most popular or most famous one, first one discovered was aspartame here, a dipeptide of phenylalanine and aspartic acid. And these peptide sweeteners are extremely unstable. So you would not be able to use them in, for instance, baked goods. You would not be able to use them in anything that has an extreme of pH either. And they hydrolyze very easily. So if you have an acidic product, or if you have a product that is heated for any length of time, then certainly aspartame would not be appropriate. The other 2 there, allotame and neotame, those have a little bit more stability. But still, in comparison with the sulfamides, which are very stable to pH and temperature changes, the peptide sweeteners are very unstable. So yeah, in comparison with all of these are very unstable. So they have limited use. You know, beverages, powder drink mixes and stuff like that, that's, you know, their wheelhouse, but any kind of baked good won't work. You can use it in like a pasteurized product. A pasteurized beverage, or say milk product, you know, chocolate milk, for instance. You could use it there because that pasteurization process is just so quick. So you'll lose a little bit of sweetness, but it will mostly be retained. Okay, next we have a couple that are chemically modified. This first one is chemically modified sucrose, this sucralose here. So sucralose is a chlorinated derivative of sucrose. And it's also very stable. So it's stable against pH and temperature. So similar to the sulfamides. This one is it's not approved for use, for one thing. So it's not going to be something that you'll probably be working with. It is made from like the flavor compounds of citrus fruits. And they're hydrogenated. These flavor compounds are normally bitter. When they're hydrogenated, they become sweet. But it's not approved, so we won't spend too much time on it. Sucralose, very popular. And then interestingly, you know, see, all of these are not, you know, they're not naturally occurring. We have these down here that are naturally occurring here that have like, they're not approved, or they have some stipulations on their approval. I think that's a little bit interesting. First we have, I have rhabdioxide A here, which is a stevioside. Probably you've heard of stevia as a sweetener. So this would be one of the compounds in, say, for instance, a stevia leaf extract. So stevia leaf extract will have several steviosides, and this is one of them. So I have this asterisk here. because they were approved very recently, 2018. Before that, each stevioside, and there's maybe 8 of them, each one had to be approved individually. And of course, to do that, then a company would have to be able to purify that single stevioside and then go through all the testing to approve it, which was very difficult. So ribadioside A was actually approved, but now basically, all the steviosides in that extract can be used in foods. These compounds, I would say, have stability in between. So the sucralose and the asulfame potassium and saccharin, those are the most stable. And then the steviosides would be in the middle. They have pretty good stability, but not as good as the others. And then finally would be the peptides here. Okay, these other ones, we don't necessarily really need to spend too much time on them. This compound, which I think is probably not something I can pretend to pronounce here, but this compound is not approved as a sweetener, but it can be used to as a surfactant. This one tastes like black licorice. Tastes like licorice compound. And then these other two, down at the bottom, these are proteins. And proteins can be sweet, but because they denature, they have limited use. Just like the peptides, they hydrolyze, they denature, and also their sweetness is way different from sucrose. So sucrose has a sweetness in your mouth and then it goes away. These protein sweeteners, at first they aren't sweet. That sweetness builds slowly and becomes very intense after several seconds or minutes, and then it stays there for several minutes. And so it's not really desirable because that sweetness doesn't clear from the mouth very quickly, and it also doesn't come very quickly. And then also the sweetness profile is very different at different pHs. So like acidic pHs, this monelin is not sweet at all. So very difficult to work with those. Not approved for use anyway. Okay, so we skip some slides and we come to blending. So first of all these sugar substitutes have some pretty strong negative properties. So most commonly, their negative properties are that they're bitter or metallic in taste. So they have a lot of sweetness, but it's accompanied by a little bit of bitterness or some metallic flavors. And also the problem of this lingering sweetness. Most of these artificial sweeteners have a lingering sweetness, which means that instead of being sweet when it's in your mouth, and then when you swallow that food, the sweetness is gone, like in sucrose. In these products, when you swallow that, the sweetness stays there for a period of time before it clears from your mouth. So one thing that can be done is we can blend a bunch of different sweeteners. And what that does is we keep the concentration of all of them really low, because each one of them will provide some sweetness to that product. And so the lower the concentration of all of these, then the less side flavors we get. And so we can keep the sweetness the same by adding all the sweetness together, but the concentration of each one individually is low. And then some actually will exhibit synergy, and that's what's shown here. So this is a mixture, and probably you've seen this on lots of packages, certainly on beverages, carbonated beverages, diet beverages. This is super common. Combination of aspartame and asulfame K. So if we blend these two, we would expect a sweetness profile like this. So for instance, here at 60% asulfame K and 40% or 60% aspartame and 40% asulfame K, we would expect a sweetness at this level here. But actually, it's way up here. So the blending of these two sweeteners together is very common because of the synergy between them. And actually, this blend here, 40% ACE K and 60% aspartame, is you can just buy that as a blend already and add it to foods. Okay, next let's talk about sugar alcohols. So sugar alcohols would be another sweetener. These are not high-intensity sweeteners. They actually have either equivalent or less sweetness than sucrose. In bold there, I have the naturally occurring sugar alcohols, and then there are a few that are chemically modified. So you see here the sweetness of sucrose is 100. Xylitol, equivalent sweetness to sucrose. The rest of them lower. So these exhibit a low glycemic index. So they're desirable for, low calorie, dietetic kind of foods. They have lots of properties that are important. Number one, they have a cooling effect. So when you put these sugar alcohols in your mouth, they have a cooling effect. So it feels kind of like, mint has a cooling effect when it goes in your mouth. So these would be similar to that. Sucrose here, an unnoticeable cooling effect. And some of these have an extremely strong cooling effect. So very commonly used in minty products, especially gum, because they have that kind of effect. Next, we have hygroscopicity, which is the tendency for these dry powders to absorb moisture from the air. So as we have higher and higher relative humidities, this is how much water is absorbed by those crystals. So a product like sorbitol here, this gray one, picks up moisture very readily from the atmosphere. So sorbitol would be very hygroscopic. And in contrast, we have mannitol here that stays very dry all the way up to nearly 100% relative humidity. And so mannitol would have very, very low hygroscopicity. Solubility is different. Some of them, so this red line here is the solubility profile of sucrose. So we see a lot of the sugar alcohols are less soluble than sucrose. But there are a few, like sorbitol, that are more soluble than sucrose. So the solubility profiles of each of these sugar alcohols are different from each other, and they're also different from sucrose. And then finally, we have water activity here. So this would be, if we are going to use these sugar alcohols, for instance, as a preservative to lower the water activity, this is the ability of sucrose to lower the water activity here in red. And we see that the sugar alcohols are more effective at lowering that water activity. So we would need to add less sugar alcohol if we wanted to add these to lower that water activity for some reason. Okay, we got 5 minutes to talk about emulsifiers. Okay, so first of all, emulsifiers, as we know, are compounds that have a polar region, denoted on this picture by a green dot, and then a nonpolar region, denoted by this squiggly line going into the oil droplet. And so this is how they are able to mix these yellow oil droplets into this water phase. So they create this kind of structure here. So that is what we usually think of. The main property of emulsifiers is that they can emulsify oil into water, and do this by forming these micelles here. They also have several other functions that I'm going to focus on today. So number one is they can be involved in crystal modification, wetting of solid materials, dough strengthening, and heat transfer and frying. So just go through two emulsifiers here. Number one, you ought to know about monoglycerides. Monoglycerides represent about 90% of the emulsifiers used in foods, and so these are very important. But they are just a fatty acid esterified to glycerol. The fatty acid can be different. This shown here is stearic acid. Lecithin would also be very common, and this one is also naturally occurring. So lecithin typically is extracted from plant oils. So as a company is extracting oil for, to sell the oil for certain reasons, soybean oil or corn oil, sunflower oil. In the process of that extraction, you extract the lecithin from those products as well. And then during the cleaning step for that oil, the lecithin would be removed as a byproduct, and then it can be sold as an emulsifier. Phosphatidylcholine is the principal compound in lecithin. There are several other phospholipids there, but phosphatidylcholine would be the predominant phospholipid in lecithin. So emulsifiers emulsify oil. They can also emulsify air. So that's really important to remember as well. So they're very commonly added in whipped products that have air incorporated into them instead of fat. And these polysorbates are very good at doing that. They do a good job of forming a film at the surface there between the air and the water in that product. Also, they can incorporate air into a batter. So you see all these emulsifiers, I have them highlighted here. So you do want to be able to pick those out of an ingredient statement. Which ones are the emulsifiers? So I have them highlighted here. And on this picture, on this graph here, it shows batter density. So of course, if we incorporate air into that batter, the density is going to go down. And we see here PGMS, which is this propylene glycol mono and diesters of fatty acids. That's PGMS. You can see that's the most common one used. And it's very effective at getting air into those batters. And so that's why in these cake mixes, we just have to put all the stuff in a bowl and stir it and put it in the oven. Right? Normally, you have to spend a lot of time beating air into fat and sugar to make a cake properly. But in this case, we put all these emulsifiers in so that the air goes in without any effort. So you don't have to use a mixer and all that stuff. Emulsifiers can change the crystal properties of fats. So we'll talk about this in fat section, but in bakery shortenings, we typically want beta prime crystals. And if we add emulsifiers, specifically mono and diglycerides, if we add those to a bakery shortening, it will keep the fat in the beta prime crystalline form. Keep it from going to the beta form. They can also preserve the quality of bread. So next week, we'll start talking about starch. And when starch crystallizes, it's called retrogradation. And when that happens, the bread becomes stale. But if we add an emulsifier, it will prevent that starch from retrograding and keep that bread soft for longer. Emulsifiers can wet surfaces. So if we have particulates in a product, if we add an emulsifier, this is without emulsifier here, the liquid will bead on the surface of that particulate, and it will seem rough and dry. But if we add an emulsifier, it's going to be able to spread over the surface of that particulate, and it will seem moist and soft. Last slide. We want, in frying, it's nice to have a emulsified shortening. So this is a donut here. And as we put that donut, if we have unemulsified shortening, of course, when we put that donut into oil, the water is coming out of that batter and going into the oil and then out to the atmosphere. And that's shown here in blue. But it creates this film on the outside as the water migrates out of that donut that is a cool spot. It's a cool spot. And so heat does not get into the donut as well. So it's going to have to fry for longer. It's going to pick up more oil. So it's going to be a greasy product. If we have an emulsified shortening, we don't have that barrier. We don't have a cool barrier. So heat is going to transfer into that donut much more efficiently. Frying time will go down. The browning on the outside will be not as severe. It won't look burnt on the outside. And also it will be less greasy because we have a shorter frying time and better heat transfer into the center of that donut. Okay, that's it. Well, if you have questions, we'll talk about them on Friday. Thanks, everyone.